Hello, I'm Marty Fayer from the Ginston Laboratory at Stanford University. Before I start talking about quasi-phase matching, I'd like to thank the organizers, Benoit and Bob, for inviting me to come to this beautiful place and to join this very interesting looking school. One technical note. There we go. Excuse me. One technical note. I have some abbreviated references on all the slides. There's a bibliography that I'll attach to the second set of notes, which has the complete references for those who care. As we've heard from several of the speakers today and yesterday, there are a rather complex set of requirements that a useful material for quadratic nonlinear optics has to meet. Some intrinsic properties like having adequate nonlinear susceptibility, birefringence for phase matching, in many cases a waveguide technology if you want to operate at low powers or with high gains. And in addition to those, there's a whole set of extrinsic technical issues that are annoying but often determine whether a crystal is useful or not. Things like its optical absorption, it's resistant to intensity damage, photo-induced aging mechanisms like photochromism and photorefraction, et cetera. And once you've found a material that meets all these criteria, in many cases it's the phase matchability that limits the range of applicability for that material. And in part for that reason, there are many dozens of crystals in various stages of development, but only a handful have really been raised to the technological level of really practical use. So an alternative to birefringence for phase matching that is more systematically engineerable is an attractive way to extend the utility of a handful of well-developed crystals, and quasi-phase matching is such a scheme. In a quasi-phase matched device, in a conventionally phase matched device of some length L with a certain nonlinear susceptibility, if we use second harmonic generation as an example of the nonlinear process in question, if we don't have phase matching, that is, if the sum of the two k vectors destroyed is not equal to the generated second harmonic k vector, then there will be an oscillatory exchange of energy between the harmonic and the fundamental with a characteristic length that goes reciprocally with that phase mismatch delta k. If you happen to be able to phase match via the birefringence schemes that have been discussed already several times, then you get monotonic growth of the second harmonic intensity, and that's the most attractive situation. An alternative, as we've also heard several times in the recent lectures, is quasi-phase matching. If one imposes a periodic sign change on the nonlinear susceptibility, adding an additional periodic structure and thus an additional k vector in the problem, one, instead of conserving momentum, can conserve something like a quasi-momentum to the extent that this periodic structure is just the right k vector to compensate for the phase velocity mismatch delta k. In such a situation, the required period for this structure is proportional to the wavelength and inversely proportional to the dispersion, the difference between the refractive index and the at the harmonic and the fundamental. And in typical cases, that's a few to a few tens of microns. That's not an easy thing to build. In fact, if you're working into the visible or near UV, you're often talking about just a few micron layers here, and even in the mid-infrared, only a few tens to maybe 100 microns. And so rather than stacking up a collection of plates to make rotated 180 degrees to make such a structure, one really needs a monolithic technology, ideally under lithographic control, in order to keep the long-range order in such a structure, as well as to have some mechanically plausible piece of material when you're all done. So while that sounds difficult, finding such a patterning technique, if you do solve that problem, then you've replaced the challenge of birefringence and its limitation on the useful range of a given material, and replaced it with this need to develop a technology that's initially difficult, but ultimately gives you a systematic engineering solution. By far the best developed such material system are the ferroelectrics. These are materials with domains of spontaneous electric polarization, akin to the spontaneous magnetic dipole moments that appear in ferromagnets. And in the simplest 180-degree ferroelectric, the relationship of an up and a down domain is such that it will change the sign of the nonlinear susceptibility, just like slicing and rotating the crystal would. Techniques have now been developed where fine pitch patterns of the order of microns can be put through millimeters, or in some extreme cases even centimeter thick plates. The physics of how this process works I'll touch on a little bit, though the details are perhaps beyond the scope of this course. The techniques have been extended to full wafers. 3 and even 4-inch wafers have been patterned with high quality quasi-phase matching gratings. More recently, semiconductor materials, which are conceptually the same thing. You are inverting the structure in some monolithic fashion, but it's a very different piece of material physics than the ferroelectricity. I'll talk about some of the semiconductor techniques a little bit later in the second lecture, and how that's accomplished. And complex patterns, almost anything you can imagine on a photolithographic mask can be transferred into the structure of the gratings. In this example, it's an array of slightly different period gratings, and an expanded version of that image on the right. You can also make interesting structures. These are nonlinear Fresnel zone plates and nonlinear parabolic lenses, Fresnel lenses. I'll talk a little bit about those as well. So what are the advantages of quasi-phase matching over conventional phase matching? Again, we've heard several of these already discussed. One key one is that you can use any desired combination of polarizations for the interacting waves that are convenient for your purposes. One particularly important point is that since you aren't relying on birefringence to overcome the dispersion, and that then determining a particular combination of polarizations and propagation directions, often leading to critical phase matching and Poynting vector walk-off. In a quasi-phase match crystal, you're relying on this periodic structure to accomplish the phase matching, so you can always propagate along an optical axis, which means you always have non-critically phase-matched interactions, at least if you want them. And you can use parallel polarized radiation, which means you have access to the diagonal nonlinear tensor coefficients. Those are often much larger than the off-diagonal ones that you need to couple orthogonally polarized waves for birefringent phase matching. In the case of lithium niobate, the nonlinear coefficient for this case is 7 times larger than the one for that case, and the efficiency goes with the square of that number, so that leads to those much reduced, for example, parametric oscillator thresholds that Majid was talking about earlier today. In addition, you can now operate essentially any interaction within the transparency range of the material, as opposed to the ones where you happen to have the right balance of dispersion and birefringence. And something I will talk a lot about is that you can access degrees of freedom that don't even exist in conventional materials. By using aperiodic gratings, you can shape the spatial, spectral, or temporal behavior of the mixing process in ways that just don't exist in conventional structures. And since you can tailor one material for a large variety of interactions, it means you can focus your technological development on a handful of crystals instead of a dozen or 2 crystals, and it's a small business optics, and so you don't have a lot of capital to spend on long and tedious crystal growth development. And that's what I mean about this being sort of a family of generic nonlinear materials. Much like silicon is the semiconductor you use for the vast majority of electron devices, you don't come up with a new semiconductor when you want to build a microprocessor or a memory or a fast switch. Okay, so like I said, I will emphasize in large part these kind of techniques because, well, I'll explain why later. just a look at some typical properties of a few commonly used birefringently phase-matched materials versus quasi-phase matched materials. For example, lithium niobate, the nonlinear coefficient used for birefringent phase matching is substantially, as we discussed, smaller than the one for quasi-phase matching. And if you look at the borate materials, they're an order of magnitude smaller in nonlinear coefficient than lithium niobate D33. Another point to note is that there are some new materials coming along. I'll talk a bit about those in the second lecture. Lanthanum borogermanate is a UV ferroelectric, which has recently been developed and periodically pulled by Oxide Company in Japan, and offers access to much shorter wavelengths than the typical 400 to 500 nanometer wavelengths where the conventional lithium niobate KTP type materials start to have trouble. And at the other end of the spectrum, orientation pattern gallium arsenide extends transparency well into the mid-infrared. The 3-phonon peak is around 12 microns, and you can go much farther than the limitations imposed by multi-phonon absorption on the common oxide ferroelectrics. Okay, so just a snapshot of a few of the kind of things that I hope we'll have time to touch on over the course of the next couple of lectures. One kind of use of these materials is, just as we've discussed, better the conventional materials, non-critically phase-matched, large nonlinear coefficients. Here, ytterbium fiber laser is being doubled into the yellow, and it, for not very good reasons, is illuminating a lemon, but it looks nice in the picture. As I mentioned, you can make more complicated patterns, like multiple different QPM period gratings on the same chip, and if you do that, you can put that inside an OPO cavity. And as you translate through these different gratings, you get different phase-matched pairs of wavelengths, and you can tune this one device from 1.3 to 5 microns with a 1.1 micron pumped OPO. As I said, aperiodic gratings offer some interesting opportunities. The point there being that you can phase match a range of wavelengths that is set by the range of grating K-vectors in this chirped grating, and different spectral components, for example, of a pulse, will phase match at different points in the grating. This particular color might phase match here, another color might phase match there. And an important point is, because the group velocity of the fundamental wave compared to the harmonic wave is generally quite different, it means that there's a variable group delay for these different colors, and by choosing the chirp rate of this grating, you are choosing effectively to engineer a certain extra group velocity dispersion into your problem that can be used to stretch or compress a pulse at the same time that it is being frequency converted. Can also be used to engineer very wide bandwidth optical parametric amplifiers. Some work we've been doing with Ursi Keller's group. Few cycle, 3-ish cycle pulses in the mid-infrared have been generated with reasonable pulse energies and high repetition rates. I'll talk about this OPCPA scheme later on. It again takes advantage of a chirped grating to get wide bandwidths in collinear operation, even though it's a non-degenerate case. You can also do interesting things with so-called cascade nonlinearities. You can get nonlinear phase shifts that scale with the square of the chi2. They involve a forward and a backward mixing process, and inversely with the phase mismatch delta k, so that you can engineer trajectories of an effective chi3 into a material via the trajectory of delta k that you program into it via a chirp grating. And among the kinds of things you can do with that are supercontinuum generation, analogous to what's done with conventional chi3 methods. But here, for example, is a continuum extending from 500 nanometers in the visible out beyond 2.5 microns in the infrared, based on this kind of cascaded nonlinearity and aperiodic grating. if you combine with a waveguide such quasi-phase matched interactions, you can take advantage of the tight confinement over long interaction lengths to get a few more orders of magnitude higher efficiency than you even had in the bulk. And that can be used for a variety of interesting interactions at low optical powers. One that we've been doing a lot of work on lately is manipulating single photons. For example, if you wanted to detect a 1.5 micron photon with a silicon avalanche photodiode, you could sum it against a classical 1.3 micron signal and upconvert these photons one by one into the sensitive band of a silicon APD. And that process has been done in such waveguides with greater than 99% conversion efficiency, taking advantage of the combination of the large guide 2 and some features of the waveguide confinement that I, again, hope we'll have time to talk about. Okay, so an outline of what I plan to do. It's probably optimistic, but if you're pessimistic, you never try these experiments. Start off with a little bit of prehistory of the field. As I get older, I find understanding how we got to where we are is increasingly interesting, and I hope you might find a little of this entertaining as well. I learned some things I didn't know about this field, or the early history of this field, just a few years ago during some 50th anniversary celebrations of nonlinear optics. I'll touch on some of the basic theoretical considerations that, that dictate what's useful, what's a useful pattern, what's a useless pattern, what tolerances do you have on what you're building, and use that to inform a discussion of how we go about patterning ferroelectrics to meet those criteria. Then I'll begin to talk about how we can use some of the additional degrees of freedom that we have in quasi-phase matching. As I said, you can shape the spectral and temporal responses, spatial responses in interesting and useful ways, and then see how some of these notions apply in some ultra-fast nonlinear optical interactions. I doubt we'll get past here with part 1. Tomorrow in part 2, I'll take a look at a little more detail at this optical parametric chirp pulse amplification, which has a number of interesting features compared to conventional OPCPA. Look at some waveguide techniques, and in particular, how this cascaded supercontinuum generation works and how it can be modeled, and some classical and quantum optical signal processing things that can be done using these high efficiency waveguides. And I'll close with some discussion of newer materials. What are some of the issues with the oxide ferroelectrics that we have now, and what we can expect to get in the ultraviolet using LBGO, and how these orientation pattern semiconductors are opening opportunities in the mid-infrared. So, prehistory. Well, we've heard a little bit of this already in some earlier talks. A year after the first laser was demonstrated, Peter Franken did the first harmonic generation experiment. For those of you who haven't read his paper, I encourage you to do so. The amount of physics he's packed into 3 pages of that paper and how much of the next 10 years of work he anticipated, it's really remarkable. It's a beautiful piece of work. You should read it if you haven't. As Majid said, his experiment involved doubling a ruby laser, non-phase matched, in a piece of crystal quartz. He already understood the symmetry requirements for second harmonic generation. Majid also pointed out the problem with the copy editor. What he didn't point out is that Joe Jordmain wrote an article a year later in Scientific American reviewing this early field of nonlinear optics, and he has the picture with the missing dots. So if you ever want to see it, look up Jordmain's article. Within a year, Bloembergen's seminal nonlinear optics paper came out. He understood the importance of phase mismatch and the implications for mixing efficiencies. And he didn't realize that one could use birefringence to do phase matching, but Jordmain and Maker came up with that idea again in 1962. This was moving rapidly in those days. While he didn't realize that birefringent phase matching was possible. Bloembergen did propose quasi-phase matching as an alternative, though the technology didn't really exist to do that very well. It's interesting to note that Franken, in 1961, actually did a quasi-phase matching experiment. He thought of the idea independently, but he never published it, one, because he said, well, birefringence is so much easier, and two, what kind of crazy person would cut up micron-thick slices of quartz and stick them together? This is just too hard to do in the real world. But he did show that you did get a periodic growth, a growth that was monotonic as you put in this stack of quasi-phase matching plates. And this is a piece from a view graph that one of his students showed at a conference in Susdal a couple years ago. So I think it's fair to say that Franken and Bloembergen independently invented quasi-phase matching, and the first real demonstration of it was done by Franken, though not published. The importance of ferroelectrics was understood early on. Miller at Bell Labs said, well, if there's ferroelectric domains, they're going to switch the sign of the nonlinearity. If we knew how to control these domains, we could get this monotonic growth, this quasi-phase matching to work, but unfortunately, no real techniques really emerged early on to do this patterning. Bloembergen got a patent in 1968 on quasi-phase matching. Like all good patents, it expired just about when it was becoming useful and techniques were emerging to actually implement quasi-phase matching schemes in a practical fashion, but I don't think he ever made a nickel off of this because there was really no good schemes in the mid-'80s, 17 years after this patent issued. People were just starting to get serious about doing the patterning. There was some early work in semiconductors too. Dewey and Hocker at MIT took a look at rotational twins, but again couldn't find out a good way to control them. Howie Schlossberg, who many of you may have worked with if you've participated in Air Force Office of Scientific Research projects in the US, he actually did make a stack of rotated gallium arsenide plates, put them in at Brewster's angle in front of a CO2 laser and looked at the harmonic generation, and sure enough, as he went from 1 to 5 plates, he went from 1 to 25 times the efficiency, so he showed again that this quasi-phase matching was correct and a way to scale efficiency, and there weren't many good infrared nonlinear materials back in that era, but still the complexity of making these kind of stacks really suppressed serious interest in the field. The first monolithic scheme I'm aware of was done by Naiben Ming and Fong in Nanjing University. And they grew a crystal of lithium niobate from a melt. They rotated it eccentrically in the melt, so the growth rate was periodically perturbed. And with a constant pull rate and a periodic perturbation, they were able to induce domains to form sort of periodically in the crystal, though of course you can imagine that this big convecting melt is a difficult thing to control to micron accuracy. And in fact, if you look at their result, for the efficiency as a function of the number of domains, the thickness of their sample, they saw that up to maybe 20 or 30 of those, which is probably, I don't know, 100, 150 microns of material, it worked okay, but then it kind of flattened out and didn't work much better and fell below the theoretical line, and that's just the disorder that came from the fluctuations in the crystal growth, spoiling the long-range periodicity of this grating. We tried something similar back during my dissertation days, where we periodically perturbed a crystal, a single crystal fiber, a few hundred micron thick fiber of lithium niobate. The steeper temperature gradients helped stabilize that structure. We could get some periodicity. We could get some red, green, and blue light generation. This was the cover of a proposal to DARPA that got us a MURI that paid for a lot of the early work in this field. But I didn't show it. But again, the useful lengths were of order of a millimeter. And again, the disorder would creep in and make longer devices not possible. there's Dieter Junt making a couple of watts of green light in such a melt-grown fiber. The next important step was the first real lithographically patterned scheme, a method where you do photolithography to control the pattern, and hence you get long-range order as good as the quality of your photolithographic mask. In this case, diffusion of titanium into the surface of a lithium niobate wafer allowed, induced domain reversal. The physics of this is a long story and not very interesting because the technique is not really used anymore, but it allowed demonstration of a real quasi-phase matched experiment done with a real modern fabrication technique. The first experiment was simply coupling a 1-micron laser into a planar waveguide containing these shallow domains, 4 different periods because we didn't quite know the dispersion of the waveguide, and then looked at the prism-coupled output, and sure enough, the light's going the other way now. The light came in here, and on the 3rd grating, it lit up and made green light. So we said, wow, we've seen quasi-phase matching. It was an exciting day. And the Royal Institute, Frederick Laurel, Jonas Vebjorn, came up with essentially the same scheme in essentially the same year, and we both reported this at the same nonlinear guided wave meetings in Houston in 1989. So again, 2 independent groups came up with this thing at the same time. Quickly, channel waveguides emerged. Oops, channel waveguides. Blue light generation. A lot of the driving force was that this was prior to the advent of gallium nitride lasers, and there was a lot of work figuring out how you could make a compact source of blue light for things like optical data storage by doubling infrared semiconductor lasers, and so you needed an efficient compact device. And so getting to 400 nanometers here was of interest, and again, similar work nearly at the same time in the Royal Institute. And KTP was periodically polled, though they didn't know it at the time, by Laurel and Bierlein at DuPont. And then Sony came up with the next big step, which was to put an electrode structure, a periodic electrode on one face, a uniform electrode on the other face, and apply a pulsed high voltage to this thing, and domains went all the way through this wafer. So that was the first volume polling scheme that actually worked. Didn't work real well. I think this was only done on 100 micron or so thick wafers, but it proved the point. A paper that doesn't get acknowledged very much, but Bill Burns at NRL extended the Sony work and pulled some thicker pieces and actually demonstrated bulk visible light quasi-phase matched SHG in, was that 93? 94, sorry, 1994. And then the first really systematic study of how this domain formation occurs, how to control it, how to apply it to macroscopically thick wafers and full wafer processing was done by Larry Myers and Greg Miller at Stanford. And they built a crystal in which a bulk OPO was operated in 1995, and a waveguide OPO was published by Mike Bortz at the same issue of Optics Letters. So that was another exciting period in our history. And then Greg extended the technique to visible light period gratings, 6 microns, again through thick wafers, and he too was very pleased. Don't do this, it's not legal. Should have safety glasses on. But he was sufficiently pleased he wanted his picture without the safety glasses, so he promised to keep his eyes closed. We were okay. Okay, so after that, I mean, this is all the history. I mean, then thousands and thousands of papers have emerged since that time, and we aren't going to go one by one through them. You'll be relieved to know. But that's a snapshot of how we kind of got to, oops, a little prehistory, how we got to where we are. Okay, so some theoretical considerations. If you don't listen to anything else in this talk, you should listen to this slide if you want to understand quasi-phase matching, because it's a useful heuristic picture that's actually quantitatively correct as well. So what's the basic model here? So we've got a crystal of a certain length, a certain nonlinear susceptibility, and a certain phase mismatch. And we know that we've seen from a few of our earlier talks that the evolution equation for the generation of second harmonic in that crystal depends on the nonlinear coefficient, the square of the input field, it should probably be E omega, not EW. Uh-oh, a few font problems emerged. I thought I got them all. French fonts aren't the same as American fonts, apparently. And the phase mismatch, e to the I delta kz, just the difference between the k vectors of the interacting waves. So if the pump is undepleted so that we can treat this thing as a constant, we can integrate this evolution equation, and we see that the generated second harmonic at the output of the crystal depends on the integral over the length of the crystal of the nonlinear coefficient times that phase mismatch factor. Well, this probably looks to you like the Fourier transform with a nonlinear coefficient distribution, right, with spatial frequency delta k. And in fact, that's true. The nonlinear frequency conversion depends on the Fourier coefficient of the nonlinear susceptibility at the frequency, spatial frequency, equal to the phase mismatch delta k. So why is that a useful way to look at this thing? Well, if you have a uniform medium that you're probably going to birefringently phase match or something, you're not quasi-phase matching, the nonlinear coefficient distribution is simply a top hat of length L and height D. And the Fourier transform of that, as you probably know, oh, man, another one snuck in there. Sorry, ignore the mu. It's a sink. Oh, man. It's a sink with delta, geez. Just think delta whenever you see capital D and we'll be okay. It's a little disrupting when you're trying to talk about it, though. Okay, so the Fourier transform of a top hat is a sink. The argument here is delta k L over 2. The longer the medium is, the narrower the spectrum around, the narrower the spectrum is going to be, this Fourier spectrum of the nonlinear coefficient. And the longer the crystal is, the height of this of the square of the field will go with the square of the length. So we have a sink whose height goes like L squared, whose width goes like 1 over L, and importantly, it's centered at delta k equals 0. That is, only when delta k is 0, when this is phase matched, are you going to see significant efficiency from a uniformly poled, a uniform crystal, which is why phase matching is required, right? We have to sit under this curve, so you only have a small tolerance for phase mismatch, as Benoit talked about in his talk, and the longer the crystal is, the smaller the phase mismatch tolerance. Okay, so how does quasi-phase matching change this argument? Well, the nonlinear coefficient distribution is essentially this same top hat of length L, except it's now modified by a periodic sign flip, right? Well, what's the Fourier transform of the product of a top hat and a periodic function? Well, of course, it's just by the Fourier shift theorem, it's this same Fourier transform just shifted by k grading, right? So instead of being centered at delta k equals 0, our Fourier transform is now centered around delta k equals k grading, which is just our quasi-phase matching condition. So one way to look at this whole story is you're trying to create a Fourier spectrum that, oops. Geez, I must have hit the fast forward button. Didn't know we had one. You are engineering the Fourier transform of the nonlinear coefficient distribution to have a peak somewhere in the vicinity of the phase mismatch of your crystal. But of course, this is more general than what I said, and if you had some aperiodic function, some chirp function, you can still Fourier transform it, and you can still understand the spectrum of the phase matching and its behavior by these kind of Fourier arguments. And I'll rely on those several times as we go through the talk today. But for a periodic structure, it just shifts this sinc from delta k equals 0 to delta k equal k grading. Okay, so let's look a little more at this Fourier picture. Let's imagine that we can, as most of our quasi-phase matching media behave, there's only two choices. You can have plus or minus d effective as you go from an up to a down domain. You don't have continuous range of values in between. So we can describe our modulated nonlinear coefficient by some function g that goes between -1 and 1 with some period lambda, the sum of the up and down domain lengths. So we just said that our generated field will go like the Fourier transform of this thing, so it will just go like the integral of this function. We'll call that capital G in the Fourier transform domain. If our structure is periodic, as it is in the simplest cases, we can write it as a Fourier series with Fourier, with spatial harmonics of the fundamental fundamental spatial frequency 2 pi over lambda, and each integer overtone of that will have a weight in our Fourier series for that function. So usually you choose this, as we discussed, to put one of these spatial frequency components equal to delta k or close to delta k, and it will then dominate this integral, and usually you can ignore those other Fourier components that aren't close to phase matching. So if we do that and we put our expansion into our integral here and keep only the term that's close to phase matching, what you find is that the second harmonic field looks just like it would have had this been a phase-matched medium with two changes. One is, as we said, you don't want phase matching anymore. You want delta k equal to one of these grading k vectors, k sub m, Fourier components, k sub m. And the other is, instead of having a nonlinear coefficient d effective, the thing out front is reduced by whatever this amplitude g sub m of this Fourier component of our grading is. And we'll take a look at that in a second. So with these two transformations, you take d effective equal to g sub m times d effective, and you take delta k to delta k minus k grading. Everything you know about uniform birefringently phase-matched crystals is roughly correct, or almost mathematically identically correct for the quasi-phase-matched case with a periodic grading. So if we have an ideal choice where one of these k vectors is exactly phase-matched with our particular process, that's known as mth order quasi-phase matching if it's the mth spatial frequency component of the grading that's doing the phase matching. And in order to accomplish this, that's the same as saying the period of our grading is not equal to twice the coherence length. It's 2 times m times the coherence length. You could have a longer period grading and use one of its higher spatial frequency overtones as this higher order phase matching. So if we take the simplest case where the up and the down widths are equal, that's L plus equals L minus, you find that when you evaluate this Fourier series, that this coefficient is 2 over pi times m for odd m's, and it vanishes for m even, which says that the effective nonlinear coefficient that you're going to use in a quasi-phase matched case is smaller in the best of all worlds if you're doing first order quasi-phase matching, smaller by 1 over m, smaller by 2 over pi. And then if you use this higher order quasi-phase matching, it says that you're going to further reduce the effective nonlinearity. The third overtone, you have 1/3, the fifth overtone, 1/5 as much effective nonlinear coefficient. We'll see a physical interpretation for that in a minute. This is just a plot for a 50% duty cycle grading. You see that you have the largest effective nonlinearity for the m equals 1. It vanishes for m equals 2. It's 1/3 the size for m equals 3, etc. If the lengths are unequal, if L plus is not equal to L minus, if you do your Fourier series carefully, you find that instead of just 2 over pi m, there is something a factor sine of pi times m times the duty cycle. That is the ratio of the positive thing to the total period. And the implication of that, for example, for a 25% duty cycle grading, is that you can now have non-zero even order, or sometimes vanishing even orders, just according to this sine pi md over m factor. And so for odd m, the ideal duty cycle is 50%, equal ups and downs. For even m's, the optimum duty cycle, it turns out, but if you stare at that for a minute, it's 1 over 2m. Let's see, and in both those cases, d sub m then takes that form. It's reduced by 2 over pi m compared to the physical nonlinearity of the crystal. So let's see how that comes about. Well, for the m equals 1 case, we've already seen what happens. Every time the waves get out of phase by pi, we flip the nonlinear coefficient, and we get this kind of growth. And that leads to d1, 2 over p, lovely, 2 over pi times d effective. Let's look at m equals 3 case. So what happens? We said that now instead of being 1 coherence length long, a domain is 3 coherence lengths long. So after the first coherence length, you've generated some field. After the second coherence length, you've destroyed it all. And then on the third coherence length, you've created 1 coherence length's worth of second harmonic. You do the same here. You create something, you destroy something, and then you generate 1 coherence length's worth. So that's where the 3 came from, the threefold reduction in the effective nonlinearity. You've just wasted the first 2/3 of each period in this forward and backward process, and you use the last third. If you're doing 5th order quasi-phase matching, you would waste the first 4 and then use the last 1, and you would have 1/5 the effective nonlinear coefficient. So in real space, it's maybe more intuitive than in reciprocal space here. But on the other hand, if you want to do the quantitative calculation for what it is for some oddball case, you can do it. And finally, there's 2 reasons you might use high-order quasi-phase matching. One is if it's hard to make a fine enough period structure, you can get away with a longer period if you're using high-order quasi-phase matching. The price you pay is that you're losing nonlinear susceptibility. Another reason you might fool around with duty cycles is sometimes there are parasitic processes. You want to do second harmonic generation of 1.5 micron light to make 750 nanometer light. It turns out that summing 1.5 and 750 to make the third harmonic is accidentally, in lithium niobate, almost third order quasi-phase matched. So you have this other process going on that you wish wouldn't go on. But if you engineer your choice of duty cycle, for example, at 33%, then you exactly zero out that third order Fourier component, and it won't bother you. The price you pay, again, is you'll have a bit of a reduction of the first order coefficient because you didn't use quite the right duty cycle. But you have this ability to engineer the relative strength of these different components through choosing the duty cycle of the grading. Okay, so this is just a graph of some typical oxide ferroelectrics, lithium niobate, lithium tantalate, KTP. And this is the coherence length as a function of fundamental wavelength for SHG, ranging from 3.5 microns down to 0.5 micron. And you can see they're all more alike than different. In the infrared, 30 to 50 micron kind of coherence lengths. In the visible, they're getting down into these microns or approaching submicrons, which is often a challenge. If you blow up that piece in the visible, you can see now as we talk about doubling 1 micron or 0.8 microns, you're getting down to 1 or 2 micron coherence lengths, and that can be a technological challenge to fabricate. We'll talk a little more about that later. Okay, Benoit talked in some length about the acceptance bandwidths and tuning rates for nonlinear processes depending on temperature or angle or whatever variable you happen to be controlling. And one can do the same calculations for quasi-phase matched interactions. I won't walk you through all of that. The concepts are identical to the ones that Benoit talked about. The only difference is If you remember, he looked at how delta K depended on some parameter C, where C might be temperature or angle or whatever. And that just depended, in his case, on the material dispersion. If you're quasi-phase matching delta K that enters into the problem, remember you subtracted off a grading K vector. So if a grading K vector depends on this physical parameter, it will enter into the tuning or bandwidth behavior. So you can take any of the results that Benoit had and just read them over by including the appropriate dependence of K sub m, the grading K vector on the parameter. So as an example, for the spectral bandwidth, the expression for the spectral acceptance contains what Benoit had, but it also contains this thing, which is the difference between the refractive indices at the harmonic and at the fundamental. And in a phase-matched interaction, of course, this vanishes. But we aren't phase-matched. We're quasi-phase matched. So there is a difference between N2 and N1. So this term is going to appear in the quasi-phase matched case, unlike the birefringently phase-matched case. And that, another way to look at it is you're depending on the difference in group indices, group velocities, in both cases, but in the birefringently phase-matched case, the phase velocities are matched, and it's only these derivatives that lead to some difference. But in the QPM case, even the phase velocities are mismatched. Okay. Temperature bandwidth, the same kind of story. Now the point is the thermal expansion coefficient changes the length of your grading. And so that comes into how the system will temperature tune. So you need to include this bit in your calculation if you're going to do that. Okay, and let's not go too deeply into that. It turns out angle tuning is a bit controversial. I have my ideas. Benoit has his experiments. They don't quite correspond. So at least one of us is wrong. Maybe both. Without getting too much into the details of this, because it's just not that important, but there's one interesting physical feature that's at least predicted and maybe we'll observe someday. If you have a grading, if you're coming in at an angle to a quasi-phase matching grading, so the grading K vector is going one way, your pump beam is going a different way, then the nonlinear polarization contains the two fundamental K vectors and the K vector of the grading, and it says that the second harmonic should be generated on the line that connects those, that closes that triangle. That says that the phase velocity of the harmonic will not be parallel to the phase velocity of the grading, of the pump or the grading. It's this trigonometric combination. And that's a phase velocity walk-off. If you remember the Poynting vector case where you did critical phase matching in a birefringent crystal, the K vectors lined up, or at least they did if your drawing was better. But because the Poynting vector was not parallel to the K vector, you had separation again of the harmonic and the fundamental, but this was a group velocity effect rather than a phase velocity effect. So we'll report back if we ever agree on what the right answer is for this tuning behavior. Let's not go into those expressions. They're not crucial. You can do angular acceptance expressions. Again, the details are in this paper. As I say, these little short notations are expanded in the bibliography if you want to track that down. Okay, so an important feature of using quasi-phase matched materials is they have one additional degree of problem that you don't get in uniformly poled materials, which is you could have a perfectly uniform crystal with perfectly uniform linear optical properties, no striations, no gradients, no anything. But if the quasi-phase matching grading you impose on it is not perfect, then you've got an imperfect nonlinear structure. And understanding the additional effects of these quasi-phase matching errors is useful for understanding why your experiment isn't working quite the way it's supposed to. It was only a couple of years ago we figured out how we were getting excess quantum noise or excess noise in a quantum frequency conversion experiment, and it had to do with quasi-phase matching errors. So it's worth understanding a little bit about how these things impact the behavior of a nonlinear mixing process. So what am I talking about? Well, this is a picture of a not very good grating, and you can see some of the lines are a bit wider than the other lines. There's a couple of missing domains. It's not a very good grading, but it shows some of the kind of problems that can emerge in a real patterned material. So one way to look at that quantitatively is to say, here's our ideal structure. It's supposed to have a bunch of interfaces, Z1, Z2, Z3, where they nominally belong. And then the actual physical structure has some error between the actual position of the jth domain and the nominal position of the jth domain. And so we can describe our structure by the statistics of the errors, the nature of the errors of these 10,000 domain edges, or however many your sample has got. So it's useful not to speak of the absolute thickness position error delta z, but rather what is the extra phase shift associated with that error, and that just goes like delta k times that position error, or equivalently pi times the position error compared to the coherence length. That tells you what fraction of a pi your phases of your waves are wrong when they hit that interface instead of being perfect as they would if it was where it belonged. So you can show, and it's again in that 1992 paper, that the ratio of the actual generated field in such a structure with errors compared to an ideal field goes like the sum over all the domains of these position errors. So if all of them vanish, each of these terms is 1. You sum from 1 to n. You have n divided by n. A perfect structure, this is just 1. And the reduced efficiency goes like the square magnitude of this thing. And so, of course, it just will also approach 1 as you have a perfect structure. So the question is, what happens if you have an imperfect structure? And you have to evaluate this sum for some real errors. So one of the simpler things that can happen is a domain cannot form, or it can close over during fabrication. So instead of having up, down, etc., when you flip this down to an up, you have one domain that's 3 coherence lengths long instead of 3 domains, each 1 coherence length long. So that means that your sum has lost 2 domains for each one of these missing domain flips. And on the other hand, each of the edges that survives is perfectly placed. So this thing is still unity, this e to the I phi. And so you just have fewer domains. And when you do the sum, you find that if you have m erroneously flipped domains, or a fraction m over n of erroneous domains, the efficiency is reduced by this factor. And if you work that out, if 5% of your domains are missing because of poor fabrication, you lose about 20% of the efficiency. So you can tolerate a few missing domains, but you don't want to tolerate a lot of missing domains, or rapidly this factor gets small and your device is not very good. More common than missing domains, at least in the modern era, are random errors in the position. That is, you have all the domains you're supposed to have, but the edges aren't quite where they belong. So if we define the error in the length of one of these domains, oh dear, what did I just do? Error in the length of one of these domains is just the difference in the position here to here. Then there will be some distribution of domain thicknesses. And I'm sorry, my thumb is too big. Typically, the expected value of these is 0. They're randomly too long or too short. But they'll have some variance in the length of these domains associated with these errors, and that we'll just call sigma sub L. So there are 2 kinds of domain errors. The kind that afflicted melt-grown crystals and made them work so badly, it's like stacking up a bunch of coins of slightly different thickness. The more coins you stack up, you're sort of randomly walking this edge away from where it belongs. The more domains of random error you stack up, the farther the jth interface is from where it belongs. You could call that a random period error. The other possibility is the long-range order is perfect because it's set by a lithographic mask, but during the formation of the domains, the edges don't quite line up with the edges of your mask. A little jitter in the domain formation. That you might call a random duty cycle error. Those are more common in the modern era because people don't usually melt grow these things. They're done lithographically patterned. And so let's just focus on that case and skip the, oh, wow. That is a particularly interesting font error. Measured in angstroms, apparently. And h bar, the expected value of h bar might change. It's an interesting piece of quantum mechanics. Yeah, some people think fundamental constants are slowly changing in the universe. Maybe that's what we're seeing here. OK, I'm sorry. I swear I looked this whole thing through on this computer. It works on my computer. OK, so what this meant to say, these S's are meant to be sigmas, the variances of the domain positions. And this thing is supposed to be eta. That's supposed to be the efficiency. So what do we see? We expect the efficiency to grow with n squared if the thing is perfect. If there are duty cycle errors, depending on how large this variance is, you reduce the peak efficiency. The tolerance isn't too tight for that. If you work out what would reduce this thing to 1/2 of its nominal efficiency, you can have domain width errors, statistically speaking, that are about 1/3 of a coherence length and still retain 50% of the efficiency. An important thing that we didn't realize the importance of is this piece here. This piece vanishes when the domains are perfect, right? This sigma goes to 0, this bracket goes to 0, there's nothing. If sigma is large, this just becomes 1, and it says the efficiency looks like a bunch of random domains. That is, if you add up a random walk, it grows like n, not like n squared, right? And so this thing turns out, as we'll see in a minute, to be quite important in determining the behavior far from phase matching. We'll see why that's important in a minute. But for the case of random duty cycles, the effect on the peak efficiency is usually not too serious. It's really this off-peak story that we'll see is important. All right, since the fonts are all screwed up there, let's not talk about that further. Let's look at this behavior far from phase matching. This can be important. Well, we'll see why it's important. But those of you who have built, for example, OPOs in periodically poled materials have probably seen that in addition to the colors you expect to come out, it lights up like a rainbow. You get the second harmonic of the pump, you get the sum of the pump and the signal wave, you get all sorts of colors coming out of this thing. And for the longest time, we didn't understand why that was. And as I said, we also saw some excess noise in some quantum frequency converters, and those too can be related to this same effect. So what is the effect here? Let's take a slightly different look at our erroneous pattern. If this is the ideal pattern here, the actual pattern has edges that are slightly displaced from the nominal position. And we can view this actual pattern as the sum of the ideal pattern plus a bunch of little random ups and downs at each interface representing whatever the erroneous position is, right? So the sum of this and this equals that. Well, we can take the Fourier transform of the sum of two functions, right? That's easy. And the Fourier transform of the perfect part of this thing is basically perfect. It's this sinc squared story. The Fourier transform of a bunch of random ups and downs of narrow width is white noise, right? That's a bunch of random delta function-like things. Will give you a spectrum whose width goes roughly like 1 over one of these domains, and whose strength depends on what the area of all these domains is. So that's that n random things adding up to make a pedestal on the efficiency. So if you look at the behavior of this thing, an ideal grading, though, so here's this SHG efficiency, here's delta K equals 0. In the perfect case, you have this sink-like thing which is dying away in its wings. And maybe if there are some errors, you will reduce the peak efficiency a little bit. You won't increase the width because the long-range order is perfect from your lithography. But what you get is this pedestal, and this pedestal is this thing. And so the spectrum of this quasi-phase matching grading basically fills all of K-space. And so everything is a little bit phase matched by this grading. And that gives you all these parasitic colors in your OPOs. And as we'll see, it can lead to parametric fluorescence where you aren't supposed to have any because it's badly phase mismatched by the ideal structure. But this pedestal here can phase match processes that aren't supposed to happen. So when you're sensitive to things that are 10 orders of magnitude down from the peak conversion, which you are if you're counting photons, this pedestal can be quite important. So this is just a cleaner plot of an ideal grading, a grading with 10% error, 15% random duty cycle errors, and 20%. And you can see this pedestal growing up at levels of 10 to the minus 3 or so of the peak, which usually you don't care about, but as I say, when situations where you're sensitive to those things, it can matter. This is just to give you a sense for how big these errors might be in a real grading. This is a Zygo interferometer image of a etched grading to determine its statistics, which we measured. And this is a histogram of the width measured for a bunch of these gradings. I forget how many thousand. But anyway, 100 rather. But you see it's fairly sharply peaked around its nominal 5.8 micron period. And the ratio of the typical width error to the coherence length is about 8%. So you're somewhere in this kind of regime where the pedestal is kind of 10 to the minus 4, 10 to the minus 5 down from the peak. I think my first hour is up, yes? So, didn't we start at 1/2 past? So maybe we should pause before we go on to talk about how do you actually pattern a ferroelectric and how do these errors creep in and what can you expect when you call up your vendor on the phone and ask for a crystal? What should you worry about? How much should you pay? Okay. So we now have some idea of the kind of periods we need to impose on these crystals, somewhere between a few microns and a few tens of microns, and that we want the accuracy of the domain sizes to be maybe not worse than 10% or so of the width of the domains, so submicron in some cases. So that poses a fabrication challenge, and so while I'm not going to try to teach you the details of how to periodically pull ferroelectrics, it's worth knowing a little bit how the process works so you're aware of the kind of errors that can creep in. And when you're trying to convince your vendor to do something he or she has not done before, a little bit of knowledge can go a long way to make you sound like you know what you're talking about. So it never hurts. So a ferroelectric most simply can be visualized as a material in which there are sublattices of positive ions, these red dots, and negative ions, which are these blue dots. And if you shift the center of charge of the red and the blue here, the positive and the negative, there will be a net dipole moment on this side of the, in this region pointing, say, down. And on the other side, if the positive sublattice shifts the other way compared to the negative one, up instead of down, Then you'll have a dipole moment in each unit cell again, and it will be of the opposite sign as you had over here. And a region of one set of dipole moments is separated from another region of the opposite sign by a domain wall. That's this line here. And that's conceptually pretty similar to unit cells that contain spins. And if the spins are all aligned one way on one side of a wall and the other way on the other side of a wall, that's a magnetic dipole domain that's up or down, right, with a domain wall separating it. You can flip magnetic domains by applying a magnetic field to them. You can flip electric dipole moment domains by applying electric fields, because the energy of a dipole aligned with an electric field is opposite to the energy when it's misaligned, right? So you can try to make the dipoles align with the electric field. In addition to having this spontaneous electric dipole moment, an up and a down domain, if you think about this, Benoit was talking about centers of inversion, inversion symmetry. Well, you've basically flipped the crystal structure. If you rotated this 180 degrees, it would look like that one. And so this will flip the sign of such a 180-degree domain wall. You've changed the sign of all the odd-rank material tensors when you go from one side of the domain to the other. Piezoelectric, electro-optic, nonlinear optic, all of these tensors flip. And so if you can make an array of up and down spontaneous dipole domains in the ferroelectric, you are making the desired up and down sign of the nonlinear susceptibility that you need for quasi-phase matching. So what you need to do is figure out a way to, under good control, introduce such an array of domains. So the underlying physics is a little subtle, and as I say, there's no point trying to get into the details here, but I'll give you at least a little sketch of how one of these families of materials, lithium niobate and tantalate, they're fairly similar to each other. They have very high resistivity, 10 to the 18 ohm centimeters or something in the dark. You can get very large, uniform, homogeneous composition wafers because it's a technologically important material for surface acoustic wave devices, for guided wave modulators, for telecom and things. So millions of wafers are grown of these materials, so you don't have to worry too much about the inhomogeneity across the a given wafer of the material, which makes the processing more reproducible. Just like there's a coercive magnetic field that you have to exceed to flip a magnetic domain, there's a coercive electric field that you have to exceed to flip an electric domain. That's a pretty big field in these materials. About 20 kilovolts per millimeter you need to apply to make an up domain want to be a down domain. Excuse me. KTP is another important ferroelectric material for these applications. It's rather different. It has a much lower coercive field, but the wafer uniformity is less good, and that makes the processing more challenging. And also, they are quite good ionic conductors, and that changes how you would go about polling them. I'll focus on this one, both because I understand it better and I think the model is a little clearer for what's going on here. We can talk about this if anybody cares. It's also the case that there are different kinds of lithium niobate and recent modifications like stoichiometric crystals, magnesium-doped crystals. We'll talk a little bit about later, but they have slightly different properties than these. A good overview of the domain formation process is in this reference of Gil Rosenmans that came out a while ago. He's more of a condensed matter physicist, not an optical guy, and so he actually knows what he's talking about. Okay, so let's take a look at lithium niobate here and see what we see. This is a picture of some of our early efforts at polling. It looks fairly random because it is. But after some effort, we can now make these quite well-controlled patterns. And so what I want to introduce is a little bit of what we learned to get from here to here. The best described version of this has never been published, unfortunately, but this link here goes to Greg Miller's dissertation, where he actually does a nice job of discussing a lot of the details of how this processing works. So like I said, these materials, they have a high transition temperature between the paraelectric and the ferroelectric phase, very close to their melting temperature. In the case of lithium niobate, still very high even in lithium tantalate. So our processing is always occurring way below the phase transition temperature to the ferroelectric state. As I said, the coercive field, when you're well below the transition temperature, is quite large, of order 20 kilovolts per millimeter for both these materials. There is a large spontaneous electric dipole moment. Maybe 78 microcoulombs per square centimeter doesn't mean much to you, but it's huge. If you heat up one of these crystals and grab it with a pair of tweezers, you'll get a spark. In fact, you can spontaneously get enough electric field from the pyroelectric effect that you'll break down air. So these dipole effects are very strong in these materials, if that number doesn't mean anything to you. Like I said, they're excellent insulators, and the domains have a preferred, the energy of a domain wall is not independent of its orientation. They have 6 preferred directions related to the crystallographic axes. If you apply an electrode and try to pull this material, if the sides of your electrode line up with one of these desirable directions, you get a nice straight domain. If you are not along a good direction, well, the domains are going to find their preferred direction and not listen to you anyway. So you have to choose the orientation of the grating so that the preferred direction of a domain wall lies along the direction that you're trying to make your pattern. There's a 3-fold axis in this material, and it turns out to produce a 6-fold symmetry in the preferred directions. So the basic process one does is to pattern a periodic electrode. Actually, in our case, we usually pattern an insulator with gaps where, just photoresist, where gaps are exposed where you see the original wafer. You put that patterned wafer in this fixture here, which is filled with an electrolyte, typically lithium chloride and water, and then you apply a high voltage pulse to the liquid, which is making contact with your substrate in these gaps and not contacting the substrate where these insulators sit. And if you apply the right high voltage to this thing, you end up getting the domains forming through the thickness of the wafer and then stopping at some desired size. So why do they do that? Well, an important measurement that Greg made was what is the velocity of growth of these domain walls as a function of the applied electric field. And so this is going from 19 kilovolts per millimeter to 28 kilovolts per meter. That's the voltage applied to just across the wafer. And on an unpatterned wafer, you can just watch these spontaneously nucleated domains grow and look at how the size changes as a function of time. And if you look at this graph here, this is logarithmic, and it goes over 11 orders of magnitude. So this is 10 to the 3 millimeters per second, a meter per second velocity of these things that you're trying to pattern to micron accuracies. And this is 10 to the minus 11 meters per second. So this is 1/10 of an angstrom per second. So there's a huge range of velocities, and more than 5 orders of magnitude of this change in velocity occurs over a few percent change in the electric field. So there's a very critical dependence of how fast these domains grow on what electric field is being applied to the crystal. So how does that help us? Well, if you now go back to our picture of electrodes separated by insulators, if you apply a voltage between this electrode and that uniform ground electrode on the other side, initially, if you put a large enough field on here, the domains will start to grow. Once they start to grow past the edge of this electrode and underneath the insulator, you can no longer supply charge to this surface, right? This is connected to your power supply, so you're dumping charge there as much as you need. But out here, it's insulated, and so as the domain did I hit overdrive again? As the domain moves under the insulator, when you flip this dipole, you have a surface charge that's twice the spontaneous polarization forming here, and you can't screen it out because there's an insulator on top. And so what that does is it reduces the average field through the thickness once the domains grow past the edge of the electrode. This is an example of a calculation for a particular case. As the domain grows from the center of the electrode to the edge, the field stays constant because you're neutralizing the polarization charge with free charge on your electrode till you get to the edge of the electrode. Once the domain starts to move past the edge, the average field through the thickness is decreased by that charge forming due to the flipped domains. And you see here the charge is dropping off. And if you remember, we said that a few percent change in the field makes a 5 order of magnitude change in the velocity of the domains. So as the domains spread out from underneath this electrode edge, they stop. They self-break because they make a field that says slow down, and the slope of the velocity versus field is so large that it doesn't have to go very far past the edge before, for all intents and purposes, they stop. 5 orders of magnitude is a large difference in velocity. So if you design this thing right, the process will start nucleating some domains in the fringe field regions at the edge of your electrode. Those domain nuclei rapidly shoot across the wafer. They don't like this situation because you've got head-to-head domains, and that's a very high energy situation, lots of bound surface charge at those interfaces. They shoot through to the other side. They quickly fill in under the electrode because that just aligns them with the field, reduces everybody's energy, everyone's happy. And then they try to keep spreading, but as we just discussed, as they spread past the edge here, they will stop themselves because they reduce the average field due to the unscreened polarization charge. If you do things right, this is, I think, a 6 micron period and a 0.5 millimeter thick wafer, and these are just polishing scratches. And you can see the domains are quite regular and uniform. If you do something slightly different, you get a mess. And there are a lot of parameters that matter here. It turns out what you choose for the electrode, whether it's a metal or an electrolyte, you change the nucleation density and things like that. It's a long story. But the takeaway message might be, it's not on this slide. It is, oh well, let me just say it. Everything gets more difficult as the periods get finer. You have to have better control over everything. You need a higher density of nuclei to get the behavior to average properly over the whole wafer. There's a greater tendency for the domains to pinch off as they go through the thickness. In addition to becoming more difficult as the period gets shorter, it gets more difficult as the sample gets thicker. The physics of that is a little murkier. I can't say I fully understand why there's such a strong dependence on thickness, but there is. So the thicker a substrate you ask a vendor to pull, or the finer pitch grading you ask them to pull, the harder the job is going to be for them. And we talked about, we just saw how we have some pretty good control. If you have 8% variation on a 6 micron domain, you're speaking of hundreds of nanometers of order 100 nanometers of error in the width. So it's pretty well controlled. So it's pretty routine now to get periods in excess of 5 microns. Usable material has been produced in lithium niobate and tantalate down to about 2 micron periods. Infrared devices are more or less routine, up to 1 millimeter kinds of thicknesses. And some groups like Takanori Taira's in Japan, we'll take a look in a minute. He's pulling centimeter thick wafers with infrared tens of micron periods. By using a non-periodic mask, you can pretty much pattern into the structure any grading distribution you're interested in, chirping the grading period, transversely varying it, making a wedge. Well, wedge has some limits we'll talk about in a little while. Lithium tantalate is pretty similar to lithium niobate, a little easier to pull at short pitches. Magnesium oxide doped lithium niobate, which is a popular material, It has less photorefractive and photochromic sensitivity than the conventional lithium niobate. It also has a lower coercive field, which makes it easier to pull thicker samples, but it's also a bit more difficult a material to deal with. The nucleation of domains is more erratic. It is a leakier electrical material, not as good dark conductivity. Some reference here talk about some of those issues. And different polling techniques are required for that material. Some guys at Fujifilm did a corona discharge method, which worked okay. The so-called multi-pulse method that Dr. Tyra's group has pioneered seems to be the method of choice. We'll say a word about that in a minute. And Tyra's group has shown periods as short as 1.4 microns in lithium niobate, mag-doped lithium niobate. And they went from 3 millimeter to 5 millimeter and 10 millimeter substrates now, thick substrates, and are pushing towards 15 millimeters. But there are some issues as the thicknesses exceed perhaps 5 millimeters. Let's not talk about the details of that apparatus. This is a picture from one of his papers. So this is a 5 millimeter thick wafer, and it's looking in at the side of it, so the domains are alternating up and down here. It's not a real high contrast picture, but if you look near the top, the middle, and the bottom, you can see the width of these domains is getting wider and wider, the light-colored domains. Differential etching shows up, the plus and the minus domains. The domain width is tapering through the thickness. So if you had such a sample, the empirical observation would be if you sent your laser beam through the top of the crystal and the middle of the crystal and the bottom of the crystal, you would see a different nonlinear behavior. Basically, you know, if the middle is 50% duty cycle and gave you the largest nonlinear susceptibility, we said you wanted a 50% duty cycle, right? Then you'll do worse near the top and near the bottom because the duty cycle is different from 50% because of this taper of the width. So if you're playing around with unknown samples, it's not a bad idea to do a little bit of mapping and seeing where the performance is best, because these kind of inhomogeneities still exist, especially as you're pushing the envelope, trying to get to very thick material or very short period gratings or things like that. Yeah. We talked quite a bit about this random duty cycle jitter and the pedestal it puts on the Fourier transform. I think a lot of vendors aren't real familiar with this, so if that's an issue for you, you may need to just discuss it with them. The taper and the depth we just talked about, and both these things get worse for short periods and thick samples. Let's not talk too much about KTP polling. There are lots of people in the world who know more about it than I do. There are different flavors of KTP grown by different crystal growth methods with rather different properties: high resistivity, hydrothermal growth, low resistivity, flux growth, different homogeneity in these kinds of materials. It's a complicated story that I don't think can be summarized easily in one graph. But one important and impressive thing that has been done is the group at KTH, Laurel and Canalius, they have succeeded in making sub-micron periods in KTP. And as we will talk about probably next time, they've made mirrorless backwards OPOs using this very fine pitch grating. This is a very impressive piece of material engineering that they did there, and that's written about in that reference. Okay, so that's all I wanted to say about basics of quasi-phase matched interactions and about how you fabricate these things in ferroelectrics. And the next thing to talk about are some devices. And there's really two paths we can go by here. One would be to talk about conventional nonlinear optical architectures which take advantage of the large nonlinear susceptibility and the flexible phase matching and possibly some of the waveguide technologies developed in quasi-phase matching media. But there's 2, 4, 6, 8 talks at this meeting that are going to touch on these things. That are going to touch on those things. And in fact, Majid, much of the latter part of his talk was about these kind of conventional structures taking advantage of the nice properties of quasi-phase matched materials. The other class of things we might talk about are designs that take advantage of specific additional degrees of freedom that exist in quasi-phase matched media that don't exist in birefrigidly phase matched media. As we've said, aperiodic gratings in the transverse or longitudinal dimension. You can engineer a lot of interesting behaviors. And I think it's probably more interesting to talk about this and leave the use of the nice properties but conventional properties of the quasi-phase matched media to a lot of these other talks where no doubt you'll see a lot of that kind of material, as you saw in Majid's talk. So like I say, we'll focus here on some architectures using these additional quasi-phase matching degrees of freedom. I won't go into detail on most of them. They're more just to put these ideas into your head to give you an idea of what you might be able to use in the lab if you're trying to do your own experiments or come up with your own new architectures. But there's references on all of these slides to detailed papers where you can get more of the clarification on the issues. Okay. That was a very useful animation, wasn't it? Okay, so we've already talked a little bit about how one can use more complicated... Geez, my thumb is just too fat. It's probably eaten too much or something. Okay, how you can use multiple gratings. For example, this thing I showed where you had a 26 and a 26.2 and a 26.4 micron period gratings, all fabricated just choosing a mask that had those different patterns on it, and then translating that thing through a cavity, and you can get a set of discrete pairs of signal idlers spanning the whole transparency range out to 5 microns, and with a 1 micron pump pushing to 1.3 micron wavelength for the signal. Sometimes having discrete tuning points is advantageous because you know where you are. You just have to calibrate to within one grating period and you know what you're working with. If you want continuous tuning though, a fan-shaped grating, for example, first done by some guys at Sandia working with the Crystal Tech people. In this fan-shaped grating, you can do the same concept, but now as you translate transverse to the fan, you have a continuously varying period instead of a discrete period. The limitation in the case of lithium niobate is that fan angles bigger than about 5 degrees are hard to fabricate. The domains start to get erratic when you try to make the angles too far from those preferred orientations I was talking about. But up to about 5 or maybe a little more degrees, you can build that structure. So if you have enough aperture available, and since you have 3-inch wafers in principle you could use, you can get a pretty big range of domains even with a 5 micron spreading angle. Another thing you can do, and Majid talked about discrete versions of some of these things, is to put more than one grating in a crystal so that you can have serial operation of more than one nonlinear process. In this example from Lightwave Electronics, it's a 1 micron pumped OPO using one of these gratings, the longer grating. So the 1 micron pump and a resonated 1.5 micron signal wave plus an idler out at 3 microns. That's the basic OPO that you've got operating. The second grating sums the pump wave with the resonant signal wave to make a red wave at 630 nanometers, which they needed some photodynamic therapy or something. And the second grating is, of course, with a period chosen to phase match this process. The first grating has a period to phase match that process. The nice feature of putting both these things in one grating is that you don't have to worry about anti-reflection coatings, broadband, anything, extra losses from extra interfaces. It's still just 2 interfaces on your crystal, and the internal joint between these 2 QPM gratings is optically transparent and doesn't cause any problems with the interaction. And obviously there's a large variety of such sequential nonlinear processes you could engineer in. You can do third harmonic generation by first making second harmonic and then summing to the third, again, just by putting 2 gratings in a chip like that. So those are relatively simple examples of some of these degrees of freedom that we might want to think about more broadly. One way to categorize these things is, are you manipulating the spatial or the temporal behavior of your mixing process? And are you manipulating the amplitude or the phase of the mixing process through your choice of modification of your QPM structure? So let's look at some examples of all of these things, and maybe it'll make clearer what I'm talking about. So when you build a high-gain nonlinear device, for example, the OPA that Benoit talked about in his LBO crystal, there's a bit of a problem because your pump intensity is, unless you've engineered a flat top in space and time, is a Gaussian. The exponent is proportional to the intensity. And if the peak of this thing is large, then when you exponentiate it, it's much narrower than the original pump beam. The amplification of your OPA, the efficiency of your SHG process, whatever you're talking about. If you're in an exponent like this, when you're at the half power point of the intensity, you're at the square root of the gain. So if this thing had 10 to the 5 gain and the top of this Gaussian, it has 10 to the 2.5 gain down here, which means the gain is spatially narrower, and if this is a pulse in time, it's temporally narrower than what you're pumping with, which means you might operate efficiently near the peak here, but out in the wings, the thing doesn't work very well. And if you drive it hard enough to get the wings to start to behave usefully, now you're overdriving the middle, and you're probably going to get a back conversion process or something annoying going on. So one tool you can use to try to fix that is to manipulate what the radial variation of the gain is in your structure. And since the gain is proportional to the length, if you were to make a QPM grating that was not uniform across the aperture of your beam, but was shorter at the center and longer at the edges, just by not poling these regions, then you could make the product of the intensity and this length and the lower intensity and that length over some portion of the Gaussian beam. You can flatten this thing out. So this is a micrograph of a 100 micron such region. Oh yeah, get there sooner or later. 100 micron such region designed for a particular size of Gaussian beam. And here you see an experiment where first it was done in a uniformly poled section, and you see some SHG efficiency here. That's a Gaussian, as you would expect. And then in this flattened region, making 2 different choices of how wide a region across the Gaussian to flatten. Instead of seeing this, you see a flat and a flat. So in other words, the product of the intensity and the length squared here was conserved over a large portion of the Gaussian. So this would not fix your time domain pulsing. I mean, you're still going to have a temporal peak if you have a pulse, but you can certainly reduce the amount of radial variation in the mixing efficiency by using such a structure. I believe it was Majid talked about double passing and the phase problems you get when you double pass. If you say you want to do second harmonic double pass through a crystal, I believe his example was an OPO, but let's stick to second harmonic for simplicity. As Majid pointed out, as you go through this medium and then you bounce off this mirror and you get some phase shifts between the fundamental and the harmonic, and maybe there's some air dispersion or something, then when you come back through this structure on a second pass, the second conversion path may add in phase or out of phase or at 90 degrees in phase to the forward path, and you need some means to control that if you really want to have a double pass device operate efficiently. And there's various things you can do. You can put a dispersive wedge in there. You can do very complicated things. But one of the simpler things you can do is make this quasi-phase matching grating at a small angle to the facet of the crystal, so that the thickness of this last section slowly varies across the aperture. Since you get a pi phase shift between the fundamental and the harmonic for every coherence length in a quasi-phase match structure, as you translate this thing through the beam and you have different widths of this last stripe, you can continuously vary the relative phase between the fundamental and the harmonic that are exiting the crystal, and you can pick the one such that a round trip puts you back at the proper phase as you go through the rest of this crystal. And this is a plot of such an experiment. Here we're translating the crystal some distance. Here we're monitoring the second harmonic coming back after a second pass. And you see that if you do it exactly wrong, the forward pass is exactly canceled by the second pass and you get nothing out. If you do it exactly right, and I guess the calibration here is not very useful, but this is 4 times what you had in the forward pass in a single pass device. So you go periodically as you translate this thing from in phase to out of phase to back in phase. And so it's an easy and, again, lossless way to make this kind of adjustment available to you in a QPM structure that otherwise would require additional stuff in your apparatus. I haven't thought of a good use for this, but it's kind of cool, so I will show it to you. Something we called nonlinear physical optics. If instead of having a uniform grating, you have QPM grating, you make strips. So there's a poled strip, a gap, a poled strip, a gap. And if you illuminate this thing with a fundamental wave, you'll make a second harmonic coming out of this section, and some second harmonic coming out of that section, and some second harmonic coming out of this section. So it looks sort of like a multi-slit diffraction pattern, right? If I had just put opaque barriers and let the fundamental go through, I would have seen a diffraction pattern in the fundamental. But here, it's a diffraction pattern in the second harmonic. And by shifting the position of these gratings, of course, you can control the relative phase of this arm versus that arm versus that arm, right? Because the phase depends on the phase of the QPM grating. So what you would expect to see out here is some kind of interference pattern like a multi-slit interference. And if you take a single stripe, what you see is something akin to the diffraction pattern of a 10 micron wide slit, except this is the second harmonic we're measuring in the far field here. If you now illuminate, I believe it was 10, a pattern containing 10 of these strips, you can see what looks exactly like the multi-slit diffraction pattern of 10 things. But this is a fully nonlinear process. There's no modification of the linear properties at all here. All that's modified is the sign and position of the chi2s. So it's a fully nonlinear version of a simple physical optic device. Perhaps more neat is, what if you arrange these things as a Fresnel zone plate or as a Fresnel lens, which is, again, something well known in linear optics, but here these are, again, uniform structures in the linear sense, but their nonlinear behavior has been transversely patterned. And if you put one of these things in a Gaussian beam, say the Fresnel lens here, with the curvature oriented this way, it makes a focused beam. And if you take a look at various slices after the crystal, you see it's getting smaller and smaller, comes to a focus, and then starts to spread out again, just like a lens would have done. But again, this was just second harmonic generation with no linear property variations. An interesting feature of this, which a linear lens would not have, is if you run the light backwards, now the wave fronts are diverging, right? Not converging. And so you would expect the beam to come out as a spreading out beam, and that's what you see. The beam is getting bigger as you go away from the crystal. So it's kind of a non-reciprocal lens in addition to being a nonlinear lens, which is, again, something that linear optics doesn't provide. And I haven't thought of anything great to do with this, so if you have any ideas. But if you put this inside a standing wave OPO cavity or something, you can now distinguish the forward from the backward direction. So there may be some clever thing about outcoupling from a standing wave cavity or something that you could do with this, but we've never done anything useful. We just showed that it works exactly as you would expect from simple predictions. Okay, so those were 2 examples of modifying the space, or 3 examples of modifying either the amplitude or the phase or both in the case of those physical optics devices in space of a mixing process. But we can also mess around in the time domain or the frequency domain, temporal frequency domain, with the tuning behavior of these devices. And in order to talk about those things, it's useful to talk a little bit about ultrafast quasi-phase matched interactions. Again, Majid talked very great detail about ultrafast mixing, so I don't have to say too much here. I'll just put it in the context of quasi-phase matching, and we will also see how this relates back to our Fourier picture of the tuning behavior of these devices. So in general, the group velocity mismatch is dispersive the group velocity is dispersive, and that leads to group velocity mismatch between, say, the pump and the harmonic wave in a second harmonic generation experiment, and results in temporal walk-off. In other words, imagine I put in a pulse, a red pulse of some duration tau, and it makes a contribution to the second harmonic, which is also of a similar duration. And then as these things move through the crystal, the red light is moving with its group velocity, the blue light is moving with a different group velocity, typically slower. And so what actually happens is the pump leaves a trail of second harmonic behind itself as it moves through the medium, and the length of this thing depends on the distance you travel and the difference in the inverse group velocities. So you'll make kind of a flat top trailing behind your pump pulse if the crystal is too long. And you can define a characteristic group velocity walk-off length, which depends on the difference in the group velocities and the duration of the pulse. Larger group velocity mismatch or a shorter pulse leads to a shorter distance before the pulses separate by something like their duration. So if you look at the efficiency of a nonlinear mixing process in such a situation, if you've confocally focused it and all that kind of stuff that, again, we've heard about already, we know that the second harmonic conversion efficiency is proportional to the length of the medium and proportional to the power in the pump. So in our pulse situation, the power in the pump could be viewed as the energy in the pump divided by, it should be tau, I'm sorry, fonts have gone nuts here. Pulse energy divided by pulse duration. If we make the length of the medium this walk-off length, the characteristic length where you preserve the duration of the pulse, so it scales like we just discussed. So then, if you look at how this works out, the increase in usable length for long duration pulses is exactly canceled by the lower peak power as you make a longer pulse. And so this mixing efficiency, when you choose this optimum length for a given pulse duration, is independent of the pulse duration and is a function only of the pulse energy and the mismatch in the group indices, which is interesting. And so what it means is if you go to a shorter pulse, you'll have a higher peak intensity, which will, in principle, increase your efficiency. But just as much as you've increased this peak intensity, the shorter duration requires a shorter crystal to avoid this walk-off effect. And so the amount of energy you generate turns out not to depend on pulse duration. If you choose this condition, it only depends on the pulse energy. And so you can come up with a figure of merit for this ultra-fast kind of harmonic generation, which has units of percents per nanojoule, which is a material property that depends on the square of the nonlinear coefficient. That goes into this ordinary mixing efficiency and goes inversely with the group velocity mismatch. So you might think that quasi-phase matched crystals would be lousy for this job because they're not even phase velocity matched, much less group velocity matched. But it also turns out they have such a large nonlinear coefficient that when you're all done, if you look at the figure of merit, for example, for doubling 1.5 micron radiation, lithium niobate and lithium tantalate are actually in the range of 100% per nanojoule. You can do efficient interactions with picojoule pulses, and that's much better than LBO or potassium niobate or BBO, which have less group velocity mismatch, but they have far less nonlinearity. So when you're all done, you end up doing better in the quasi-phase matched media. We don't have to go into that. It's also interesting that this efficiency is nearly independent of wavelength over much of the transparency range for all of these common materials, which basically is due to the fact that the group velocity mismatch is getting worse with the cube of the wavelength for typical dispersion behavior, but the mixing efficiency is getting better with the cube of the wavelength because there's an omega cubed in confocal SHG. And when you're all done, it's almost flat and in the range of 100% per nanojoule. And you can do such an experiment. We did this quite a while ago with the IMRA guys, just took one of their simple low-power fiber lasers, couple hundred femtosecond pulse, doubled it in a suitably chosen length of lithium niobate in a single pass, and sure enough, the efficiency looks just about like the 90% per nanojoule that you would have expected, and you preserve the pulse duration as you would have expected. So that simple kind of argument works. So let's now tie that to our Fourier picture of how quasi-phase matching behaves. Well, fonts are still bad. That's good. We said already that the tuning behavior of this thing, the phase matching, the efficiency of the mixing for second harmonic, will be centered around delta, the K grading equaling the phase mismatch, and we'll have a width goes inversely with the length, et cetera. So how do we look at that in the case of, oops, sorry. Yeah, let's skip down a few slides here. So how would we look at that picture in the ultrafast domain? Well, now we don't have a monochromatic wave coming in. We've got a pulse. So the square of the pulse has a certain spectrum. And now how much harmonic generation efficiency each of these spectral components of the pulse sees depends on this sinc function, right? This sinc versus frequency, as we just calculated. And so you can view this as a filtering process. You have this spectrum of the square of your pump. You have this response of your nonlinear medium. So to the extent that the long linear medium is long enough that this sinc is narrow compared to that spectral bandwidth of your pump, then what you get out at the second harmonic is basically just, the sinc. It's just filtered out something from the peak of this spectrum. And if this is what the spectrum of our second harmonic looks like in the frequency domain, in the time domain, it's just the Fourier transform of this sinc, which is a top hat. And that's exactly the top hat we just found from our time domain arguments from the walk-off. So this is just a dual argument, whether you want to look in the frequency domain, it's a narrow band filter, reducing the spectral bandwidth of the harmonic and making a flat top. The longer the crystal is, the narrower this sinc function will be, the narrower the spectrum of the output, the longer the duration of the transform of that spectrum is. And that's just like the greater walk-off you get as your crystal is longer and longer. So there's an exact not just an analogy, there's an exact correspondence. You can do this problem in the frequency domain, or you can do it in the time domain, however you prefer. And we will see that we can use this same Fourier argument and this same Fourier filtering story, even if it's not a simple periodic grading. We could engineer a different passband for our crystal by, say, chirping this grading, and we could still make this filter argument. But now, of course, the thing we generate will look very different because we have altered the transfer function of our chip through the domain engineering that we do to change this Fourier transform. Before we talk about how that all plays out, we could go back for a minute and just look, let's see, with the 5-minute break, we're finishing at the 6:40, is that right? We'll get close. You never get everything done, but you know. Okay, so so this was our simple picture of a simple periodic structure. You could imagine adding other Fourier components to this structure, and instead of having one peak, you could have 2 or 3 or 4 peaks. We'll talk about how you can do this kind of Fourier synthesis in a minute, but just to show you that you can do it, these are tuning curves engineered to have 1 peak or 2 peaks or 3 peaks or 4 peaks by changing this away from a simple periodic structure. This isn't terrifically useful for what we were just talking about, but similar domain engineering can be done to make other kinds of transfer functions. So what kind of techniques exist for doing this sort of engineering? The most naive approach, and hence the one that we thought of, not the best approach, is you know that if you take the product of 2 sinusoids, forget that these are square waves for a minute, you get some indifference frequencies coming out, right? So you can make a single peak split into 2 whose separation is set by what this other frequency you're multiplying by looks like. And so if you took this pattern times that pattern, you would end up doing some more complicated domain reversal pattern that looks like the product of 2, looks like the product of 2 sine waves, and you can split this thing into 2. If you put another sinusoidal component on there, you could get 3 or 4 or whatever. And that was what was done to make this thing, was just add more and more sinusoidal components to the grating. Since this is sort of a phase-only filter, it says that the area under this curve should stay conserved. So if you split it into 2, they should be half as high. If you split it into 3, it should be 1/3 as high. If you split it into 4, it should be 1/4 as high to keep the area constant. And that's roughly obeyed here, but we have these side lobes that take some of the energy, so it's a little bit more reduced than that. But roughly speaking, you would expect to conserve the area under those curves. What turns out to be a better approach was from Isobe at NTT. Instead of doing this kind of product of Fourier components, he did a phase-modulated grating. So he took this grating, and then he slowly moved the edge away from its nominal position, and then he slowly moved it back. So it looks like phase rather than amplitude modulation. This is the particular phase modulation function he chose to accomplish a 4-peak curve. And you can see that he ends up with less side lobes than we did in our case. Perhaps Adi Aryeh, when he comes here next week or later this week, he did some work on so-called quasi-periodic structures, things akin to Fibonacci sequences and the like. And by using quasi-periodic building blocks, you could generate some complicated patterns, though I think this probably never ended up being as good as that. Chris Phillips, who was a very good student who graduated from my group a couple of years ago and is now a postdoc with Ursi Keller, he showed that you could actually convert a large family of these grading design problems into ones amenable to convex optimization. And if you can make that mapping, then you can get absolute global optimum solutions if you've defined a particular target function and a set of constraints, like you can only make plus or minus gratings, you have a certain maximum length for your structure, you have a certain minimum polling size. You can find what is the best, globally best solution. There's standard software, something called CVX out there, that if you can define your problem in this fashion, you get that as a straightforward output. This turns out to yield some very non-intuitive designs. For example, trying to design a flat gain bandwidth parametric amplifier with a target gain. You ended up, if you did a linear chirp with this kind of thing, if you made this complicated mess, you got something that just about perfect. So if you ever have to design one of these things and you really care about the performance, you might want to look up this paper. If you want to do something a little simpler and more intuitive, this phase modulation approach of Asobes is probably the next best. So let me just finish up then by tying together all this stuff about synthesizing transfer functions and time domain and frequency domain arguments in a straightforward experiment that's kind of neat, how it all works. So imagine you have a chirped fundamental pulse. Maybe it's from a fiber CPA system or something like that. And you want to make it second harmonic, and you would like its second harmonic to be unchirped, the transform limited pulse. So how might you do that? Well, imagine you make a chirped QPM grating so that different spectral components of the pulse will phase match in different sections of the grating. So in a time domain picture, what's going to happen? This slice of the pulse will go this distance at the group velocity of the fundamental. It will convert to the harmonic, and it will go this distance at the group velocity of the harmonic. A different slice of the pulse will go a different distance before it converts. So it'll be going a different distance at the group velocity of the fundamental, and then a shorter distance at the group velocity of the harmonic. So the time delay from when a spectral component enters the chip as a fundamental wave and when it exits as a second harmonic wave is controllable by your choice of the chirp rate of this grating. And you can program in a nearly arbitrary group delay as a function of frequency by your choice of grating chirp function that you put in here. So that's kind of a time domain argument for how you could create, for example, a compressed pulse out of a chirp pulse during second harmonic generation. You could also look at this in the frequency domain. If this were simply a linearly chirped grating, if we go back to our pulse, our pump pulse, it's, say, a Gaussian envelope as a function of frequency, and if it's a linear chirp, as we heard in some of our discussion of fiber optics earlier today, it's got a parabolic phase versus frequency. That's a linear frequency chirp, right? We put this into a chirped QPM grating, and we know that the transfer function of this QPM grating goes like the Fourier transform of this grating pattern. And if this is a simple linear chirp, it turns out that the Fourier transform of that is basically a flat top with some ripples on it in amplitude, and in phase, it's also parabolic in this mid-spectral region. The phase of a linearly chirped structure is quadratic versus frequency. And so if we choose the chirp to have be large enough that the bandwidth of this transfer function exceeds the bandwidth of the fundamental, then all of the Fourier components in this pump pulse will convert with equal efficiency. The product of this wide bandwidth and that narrower pulse is that pulse. So we preserve all the spectral components. And if this phase curvature is equal and opposite to that phase curvature, then the sum of those, the input times the transfer function, is just flat phase. It's a compressed pulse. So whether you look at this thing in the time domain or the frequency domain, you again get the same answer. This gives you something in many cases a little easier to design for. If you had some cubic phase on this stretched pulse, you could put some cubic phase into your chirp function as a function of frequency. So you have great freedom to design this transfer function of the chip. So if we look at an experiment trying to demonstrate this, this was about 100 femtosecond or 120 femtosecond 1.5 micron erbium fiber laser. It goes into a dispersive delay line and is stretched, in this case to 17 picoseconds. That stretched pulse goes through such a chirped Piplin crystal, and the output is analyzed. And what you find is, if you adjust this correctly, which in this case is 17 picoseconds of group delay dispersion across the pulse, when it comes out as second harmonic, it's 110 femtoseconds. So this thing did what that simple mathematical model said it was supposed to do. And in more complete detail, if you vary the amount of dispersion you add, group delay dispersion, the input pulse has a minimum duration when you have no additional dispersion here. But the second harmonic is rather long because it's added some dispersion now. But as you put in more and more dispersion on the pump, it's getting longer, but the harmonic is getting shorter because you're reaching the point of perfect compensation, and it exactly, again, follows the simple-minded theory we talked about. So let me finish up with just a couple more points. This thing was used, in fact, in an all-fiber chirp pulse amplification system, laser oscillator, stretching fiber, erbium amplifier, and then, since the goal here was to make a 780 nanometer source, sort of a TISAF replacement, using this chirp-piplin crystal eliminated the requirement for a separate pulse compressor. You could do the harmonic generation and the pulse compression in that one chip. An experiment a while ago with Lucas Gullman and Ursi Keller pushed this all the way to 5 femtoseconds. In this case, 8 femtosecond pulse from a TI-Sapphire laser was stretched by going through, I think, a pair of quartz prisms. That stretched pulse was then doubled in a suitably chirped piece of lithium tantalate, and the output was examined with, I think, a cross correlation, if I remember right. And what you got at the output was a 5 femtosecond ultraviolet pulse using this same physical concept, but pushed kind of to the limit of just a couple of cycles. I think this is the last thing I'm about to say here. Almost the last thing. I'm having too much fun. All the fonts are working. I want to take advantage of it before something goes wrong. One problem with this scheme is, unlike a conventional pulse stretcher, you can, where you have some adjustability, this guy has a fixed amount of group delay programmed into him, and you need something adjustable, like an external delay line, to hit the point where it does maximal compression. But you can make an adjustable version of this Piplin compressor, QPM compressor, by making the grading pattern vary across the chip. That is, if you have a certain chirp rate at this edge of the chip, and you have your mask and your domains with a different chirp rate on that edge of the disk, and then you just connect these lines, then as you translate your beam across the chip, you are accessing variable amounts of group delay dispersion, depending on whether you're seeing this part of the pattern, that part of the pattern, that part of the pattern. And here you can see a similar kind of compression behavior where now there's not a variable external compressor, it's just the translational position across the chip allows you to make a variable group delay dispersion in the harmonic generation process. Okay, this one's so easy, you just have to let me say it. You can do other more complicated pulse reshaping things than what we just talked about. A uniform grading, as we said, will just make a flat top pulse or a triangular autocorrelation. If you put an array of gratings into the chip and illuminate it with a pulse, each one of these guys will create a harmonic pulse. So if you have 4 sections of grating, you can take one fundamental pulse in and make a train of 4 harmonic pulses out. I forget how many were in this thing, 8 or something pulses. If you have an array of chirped gratings, then you can take a chirp pulse in and both compress it and make an array of, in this case, a terahertz rep rate pulse train. So again, it's just an illustration that you can engineer almost anything into this transfer function that would be useful for the particular application you're trying to implement. Really, the last thing I'm going to talk about here is nonlinear filtering. In many cases, you want 2 nearby spectral components in a short pulse. And there used to be some awkward efforts to like synchronize 2 femtosecond TI-SAFs with slightly different frequencies or something. That's kind of clumsy. You could make a passive filter with 2 peaks in it and just put that in your beam, but then you're throwing out a vast majority of your energy because you're only passing 2 narrow spectral features out of a broad spectrum of your pulse. If you make a 2-humped phase matching curve, you have a nonlinear filter, and any pair of frequencies that sit symmetrically around these 2 peaks of the transfer function will sum to make this frequency. So you can suck the energy out of almost all of your spectrum and deposit it into these 2 slices, or however many you want. And you can make an output that is brighter at these frequencies than your input was, because you've pulled, spectrally brighter, because you've pulled in energy from across that whole spectrum. And this is an experiment where that was done with a couple of different grating splittings, and you can get bright 2 color pulses split by a nanometer or 2 nanometers or 3 nanometers or whatever you want it to take. Okay, now I'll stop. And